this is where we left off yesterday. I showed you a video. We talked about the anatomy of a muscle. And I talked about the fact that many people believe that a muscle contracts, but the muscle itself does not contract. It has contractile units called sarcomeres that contract, and then as a result of them contracting, the whole muscle contracts. So when we looked at the organization of a muscle, we said that we had the whole muscle, and the whole muscle was made up of multiple groups of fascicles. Each fascicle was made up of groups of muscle fibers, which are the cell for a muscle, and we're talking about skeletal muscle. And then each muscle fiber is made up of multiple myofibrils, and each myofibril has multiple sarcomeres. And the sarcomere is what actually contracts in that muscle. So we discussed the anatomy of that. I also mentioned that anything that has the root myo or sarco is related to the muscle, so that you saw that. Then I wanted to show you the video of how the physiology of a muscle contraction before I explained it. All right? So we looked at the sarcomeres, and we understand that their anatomy is Z-line to Z-line, and that they are composed of both thick and thin filaments. The thin filaments are anchored on the Z-lines. The thick filaments are anchored in the middle at the M-line. The H zone is where there's only thick. The I band is where there's only thin. The A is where there's overlap between thick and thin filaments. The M line is the very middle of that sarcomere. When a muscle contracts, the Z lines come in. The thick myosin filaments don't move. They pull the thin filaments in. And then when they're done, they release them and they go back out. When the muscle needs to contract again, each sarcomere will come in and then it will let go. The thick filaments never move. Okay? So the sarcomere shorten. The contraction of the thick and thin filaments, that process is called the cross-bridge cycle, which is what we're going to review today. And that cross-bridge, each of those cross-bridges will continue to repeat formation of that cross-bridge until the muscle is done. That sarcomere is done, it will release it, and then they will slide back to their resting position when it's time to contract again, and then they release it. Okay? So that's where we left off yesterday. We call it the sliding filament theory, because the thick and thin filaments are sliding past one another. That's why it's called the sliding filament theory. Okay? Does anybody remember what triggers this series of events? What has to enter? It's calcium. Calcium enters, and this was kind of explained yesterday, but I wanted to outline it. Calcium enters. Do you remember what it bound to? Troponin. You need to know these steps. That's why I'm writing them down. Binds to troponin. Then troponin will change shape. Do you remember what it does? Troponin causes what to move? It's on the thin filaments, but it was tropomyosin. It stimulates the rotation of tropomyosin. Okay, so calcium came in, it held on to troponin, troponin changed its shape, and it caused the tropomyosin to roll over. Okay, when it rolls over, let me see, I think there's a picture. Yes. When it rolls over, so here, the calcium comes in, it binds to troponin, then it allows the tropomyosin to rotate. When it rolls over, it opens up, or it exposes, and I'm going to put this in parentheses, opens up the myosin binding sites on the actin filaments. Opens up the myosin binding sites on actin. Remember that when you see myosin, I need you to know that that means the thick filament. And when you see actin, that means thin filament. Yes. Okay, so it's done that. So those first steps were just prepping the actin, the thin filament. Then these myosin heads will hold on to those actin subunits and start to pull them. But they cannot pull anything until this has been opened up, and calcium stimulates that completely. Okay? So, I wanted to recall that. Here shows you. Wait, any questions? Here shows you Z line to Z line. You have your thin filaments anchored on your Z line. Your thick filament here in the middle, and you can see here is not contracted, here is contracted. The thick filament stays the same both times because the thick doesn't move. The H zone is the area where it's just thick filaments. The I band is where it's thin only. A is where it overlaps. So when this muscle or this sarcomere is going to contract, the myosin is going to pull the actin in, and it's going to cause the Z lines to move closer to one another. In this whole cycle, although we call the process the sliding filament, this is a cross bridge formation, which is what we're going to go into the steps for now. Okay? So here was our setup for it. Now we need to talk about when myosin binds to actin. So it opens up, it's where we left off. Then a cross bridge is formed between the myosin head and actin subunit. I'm trying to use the same terminology of the video as well, and you can find that video on YouTube. Okay? Then once it's bound to it, then it pulls it. That pulling was called the power stroke. So that's the next step. Then, so it's here, ATP has to bind to it so that it can let go. How does it say that? Yeah, ours. Okay. Myosin will detach. And I'm going to put needs ATP. And then the myosin will be recharged. Charged.
And this all happens really fast.
Yes. Like when you tell your big toe to wiggle and you wiggle it like that. Because that's literally what has to happen for your big toe to wiggle. All these steps. Hey, and guess what? We're not even finished yet. So this is when it's pulled and it's ready to pull again, because once it pulls one time, does it just stop and hold? No, it continues. So that's why it mentions that myosin is recharged. What tells that contraction, hey, it's time to stop? What has to happen? Now we do have to decide it. But what has to leave? Calcium has to leave. When we're done, calcium has to leave. Sarcomere, not sarcochlorine. Sarcomere. When calcium leaves, what changes its shape? So So calcium leaves. What did calcium stimulate initially? Troponin. It's right here. So troponin changes shape. And then because troponin changes shape, what else will slide? What does troponin move? Tropomyosin. Troponin changes shape, and the final step is tropomyosin will slide back over binding sites. So the tropomyosin will slide back over the binding site. This is from beginning to end. And it's not in your notes this way. That's why I wanted to put it here so you had a checklist, because you do have to know this. You don't have to know the neuromuscular junction like that, but you do need to know the muscle contraction. So the contraction of a sarcomere, which multiple sarcomeres will stimulate a whole muscle contraction. Okay? So I wanted to make sure that I detailed that for you. What questions do you have right now?
So that entire thing is a sliding film of glue?
From start to finish.
Okay.
Yes, ma'am. Now, the next few slides are going to show the animations of this taking place. I showed you that video yesterday, and of course you can access that on YouTube. But this is showing you calcium is bound here, so it changed troponin. Tropomyosin slid over, so the actin site, the myosin binding sites on the actin have been exposed. Here's myosin attaching. It's going to pull. And then that's the power stroke where it's pulling it. You can see that it's flexing. The only thing that's going to let that go is ATP, so ATP is going to have to bind to it again. And then it will recharge that myosin head so that it's ready to bind to that next actin opening. So here are all those together for the cross-bridge cycle that starts here. Formation of a cross bridge. And we talked about what happened before and what happened after. But these 4 steps are the 4 steps that are pictured right there. Okay. Now it's going to talk to you about this part that we did, because I didn't want to teach you this and then come back and teach you this. But it mentions that the regulation of a contraction is controlled by tropomyosin and troponin. What stimulates troponin again? Calcium. So at this point, like if we were in our anatomy class, after I taught you that this is what happened, step by step, we would immediately start talking about homeostatic imbalances. So it is very clear that you need calcium for a muscle to contract. You have to have it, period. There's no substitutions. So what happens if you have too much calcium? What if your calcium levels are really, really high? It could cause cramping. So your muscles would contract, but they would have a really difficult time relaxing or releasing that contraction. Initially, that's going to cause cramping, but what muscle do we not want that to happen to? Our heart. High calcium levels can lead to cardiac arrest. Another muscle that we don't want to be impacted by that for sure is our diaphragm. Our diaphragm pulls down so that our lungs can fill with air. And if that muscle goes into a contraction, a complete contraction, which we would call tetany, that can cause a problem as well. So too much calcium is a really bad deal. What do you think happens when calcium levels are low? It's too relaxed. Your muscles don't actually contract as they're supposed to. Can you see why this would also be a problem for your heart and diaphragm? So when we talk about, and I know that I always say multivitamins, and I'm always going to tell you that because at some point in your life you will listen to me, I'm sure. But many of you think, okay, well, I eat a pretty balanced diet. But the reality is that you don't eat good all the time. And you need to make sure that your calcium levels are homeostatic. If you get too much calcium, it's going to make you sick. But it will be really difficult for you to get too much calcium. If you don't get enough calcium, then of course you're also going to feel sick. But before you realize it, where does your body take calcium from? Your bones. Your body will break your bones down and pull it from your bones so that your muscles can contract because they need calcium. Okay? So either way, but you could definitely surpass problems by just taking a multivitamin. You have exactly enough calcium to get your regular everyday things done. And even more. That's good. Okay, so what I'm telling you right here, if calcium is not present, the myosin binding sites stay covered. So calcium is not present, myosin binding sites stay covered. What's the muscle doing? Nothing. Nothing. So calcium is not there, that muscle is not contracting. Okay, troponin is the protein that calcium binds to, and of course once it changes its shape, it will then stimulate the movement of tropomyosin. So these again are the steps that I detailed at the beginning. When we take calcium away, it undoes that. Okay. So here is the picture showing calcium being added, and then calcium, no calcium right here on the left, calcium is on the right. Okay, on this slide, excitation, contraction, coupling. We know the contraction part, but what excites a muscle to contract? We know calcium has to be present, but what tells that muscle, I need you to contract? Not hormone. The nervous system. When you say we do, that's technically correct, but being more specific, of course, you have to say the nervous system. We're talking about skeletal muscle here, muscle that you control. So when you tell, your big toe doesn't just start moving. You have to tell it, hey, big toe, move. And it will move. Your nervous system is the one that stimulates all of that. So the excitation part right here is referencing the nervous system. The contraction part there is the muscular system. It mentions that skeletal muscle cells are capable of generating and propagating action potentials. I am not going to teach you the whole neuromuscular junction in this course. That's an anatomy thing. But an action potential is the electricity generated from your nervous system that tells you to do something. An action potential is the electricity stimulated from your nervous system or propagated from your nervous system that tells you to do something. Okay? No action potential, you don't do anything. So no electricity, you won't move. Here, it mentions sarcoplasmic reticulum. What does sarcoplasmic reticulum really sound like? Sarcoplasmic reticulum. Like you've heard this before, just not with that start. Endoplasmic reticulum. So sarco is muscle. So literally, this is the endoplasmic reticulum, but for the muscle. That's all it is. And in anatomy, I teach those students in the first semester. It's just a language. Doctors and scientists want to sound really, really smart and confusing, and they're very specific. So instead of saying the endoplasmic reticulum of the muscle fiber, they say, oh, it's the sarcoplasmic reticulum. What's that? So sarcoplasmic reticulum, why this is being brought up, is because this is where the calcium for your muscles is stored. So sarcoplasmic reticulum stores, bless you, that calcium, or coughing. Okay, that's the cough, I think. Anyway, sarcoplasmic reticulum is where that calcium is stored. Let me show you what this looks like. Here's my individual myofibril. So I have multiples here. And these purple tubes that are surrounding them, This is it folded out. That's our sarcoplasmic reticulum. So the sarcoplasmic reticulum surrounds each myofibril at its sarcomere. And that's where the calcium is stored. So calcium is hanging out in here, and when that muscle needs to contract, it's right there. It releases it. The sarcomere will contract, so the whole muscle will contract. And then when the calcium leaves, it's stored there. We don't want the calcium to just be floating in our blood because it would take too long to get there. So the sarcoplasmic reticulum is where that calcium is stored so that the muscles can contract very quickly. Questions on that? Okay, when you see the term neuromuscular, what two things are being combined here? Nervous system and the muscular system. So this is where nervous meets muscle. And we're talking about skeletal muscle, so is this voluntary or involuntary? Voluntary. The neuromuscular junction is the junction of a motor neuron. Can you tell me what motor means? That we're going to be moving. Nola. Thank you. Motor means that it's going to cause movement. So you have two types of neurons, sensory and motor. So motor tells us to move, sensory gives us that information. So the neuromuscular junction is where a motor neuron meets a muscle fiber. If you've been in psychology, then this next part is going to be happy to you, because you probably already recognize it. The neurotransmitter that tells the nervous system, it communicates from the nervous system to the muscular system. So the neurotransmitter that's released at a neuromuscular junction is acetylcholine. Acetylcholine is what stimulates that sarcomere to contract. So the nervous system has electricity. It releases acetylcholine. The sarcoplasmic reticulum will release calcium, and then this takes place. So it goes electricity, acetylcholine, sarcoplasmic reticulum, calcium. Here. This is just telling you what happens before that. I do not want you to have to be familiar with the specifics of the neuromuscular junction, because I'm literally teaching you this in one whole week. So we're just really worried. All I really want the takeaway from is the muscle, because that's what this test is over, the bone and the muscle. That's why I'm not going to spend a super ton of time. Here's a neuron, part of the nervous system. Whenever electricity comes down this neuron, it stimulates these vesicles full of acetylcholine to be emptied into this open area. Here's my muscle fiber right here. Calcium binds here to our ACH, not calcium, acetylcholine binds to our ACH receptors, and it opens them up, allowing for sodium and potassium to be exchanged. Again, you aren't going to have to know that in detail. I just want to explain it in case you're watching the video or something, and you're like, what do we need to know on that? Okay? Now, last topic I want to cover today, and then we'll stop, are the types of muscle fibers you have. You have fast fibers and slow fibers. What do you think the difference is? Yeah, one's fast and one's slow. The benefit of having fast fibers is that they contract really quickly, but they also tire very quickly. So they contract fast, but they tire fast. Slow fibers are slow to contract, but their duration is longer. Okay? So they have the same amount of force, it's just the speed at which they respond. Speed at which they respond. Okay? The difference between white meat and dark meat on all animals. Oxidative fibers. Oxidative contain multiple mitochondria. What are they used for again? ATP. Mitochondria are used to generate ATP. In order to have lots of ATP, you have to have lots of blood. Why do you have to have lots of blood to that area? Oxygen. You need a lot of oxygen to that tissue. So high mitochondria means high ATP, but high ATP requires a whole lot of oxygen. Oxygen comes through the blood. So when you have a muscle that is dark, it's because there's a whole bunch of blood flowing through it. The reason there's a whole bunch of blood flowing through it is because there's a whole lot of mitochondria and there's a whole lot of ATP generated. So this is a muscle that does a lot of work. These will be our dark muscles. When you are eating dark meat, that is oxidative. Those are oxidative muscle fibers. Let me explain what white meat is and then I'll explain some examples. White meat has fewer mitochondria, probably because why? It doesn't do as much work. Its oxygen levels are probably a little bit lower. Okay, blood still flows through there for sure, it has to. But it's just got a lower energy requirement because it doesn't do as much work. This is white meat. So like chickens, their breast meat is white because they don't fly. So they don't use that muscle. That same muscle taken out of a duck is what color? Brown. It's dark meat because ducks fly. They use it. Anyways, so when you're comparing the colors of the meat, that tells you whether that organism uses that muscle a lot or not. So the lighter meats are not used, the darker meats are used more. And they're used more, as a result they have more blood flow, more mitochondria, and generate more ATP. So that's why it's a darker color. Okay? This is where I wanted to get us today. Any questions? All right.